Example of metric tensor, and now we will discuss for polar coordinate. If I am in 2D polar coordinate and 2D Euclidean coordinate, then the metric will be very simple. ds square equal dx square plus dy square. But imagine I need to jump to polar coordinate. Then the metric, I know the relationship between x and r and x and theta and y as a function of r and theta, which is x equal r cosine theta and y equal r sine theta. And in this case, dx will be written as cosine theta dr minus r sine theta d theta, and dy will be written as sine theta dr plus r cosine theta d theta. Then the ds square will be dx square plus dy square, and I have here some term which go vanish, and other term I can use the trigonometrical relationship, which is cosine square plus sine square equal 1. Then I can rewrite ds square in this polar coordinate as dr square plus r square d theta square. So here the metric is not couldn't be written as delta mn dx mdx n. That's why it is not non-flat. I mean, it is. We cannot say it's not flat. I mean, it's flat, but it's written in non-Cartesian coordinate. So the metric here, which could be written, since it is covariant tensor of rank 2, it could be written as a matrix, and this matrix is G, for example, GRR, GR theta, G theta R, G theta theta. And since I don't have a term of d theta dr, then gr theta g theta r equals 0, and grr equal 1, and g theta theta, which is g theta g theta square, is equal to r square. This is the relationship of the metric in this case in polar coordinate. What physically mean that I don't have off diagonal element? I don't have this element. That means that the lines of constant r are perpendicular to the lines of constant theta, and this is what I have in polar coordinate if they represent a flat. So this is the case, and we notice that this matrix, which is 1 0 0 r square, is invertible, and it is symmetric and invertible, and its inverse is 1 0 0 1 over r square. We will discuss now what does that mean. It is symmetric and it has an inverse, so the product of the two g minus 1 equal to identity, and symmetric means that gig equal to gji. Why I take that, and why it is symmetric? Actually, in general, it shouldn't be symmetric. I mean, but it's not wrong to take it symmetric. Why? Because I am dealing in commutative space. That means dxi dxj equal dxj dxi. That's why I can choose it symmetric to simplify my life. But in general case, there is no reason. Just accepting that it's simplify the life. There is no reason. And it's because it's commutative space, then because gig plus ggi dxi dxg, then we can split this gig ggi to be equal without losing any generalities, and this is the important idea here. Now we will have some ideas, or we will discuss some arithmetic operation on tensor. In general, it's not possible to add two tensor except if they are of the same type. Of course, because every tensor has its specific rule of transformation from one coordinate to other. And when I add two tensor from two different types, it is it is as if I am at car with an apple. I say a car plus an apple, and this is not possible. So this is not because they must be in the same object, the same type to be able to add them. If a tensor is equal 0 in one coordinate system, that's true in all coordinate system. And this is the global idea of coordinate system of tensors. It's a secret of its powerful aspect of it. Because now, if there is certain relationship, for example, if omega Vmn, which is contravariant of ring 2, equal WRS, which is contravariant of ring 2, in one coordinate system, then this relationship is true in all coordinate system. So the qualities of tensor are the same in all coordinate system, regardless the fact that its components are different from coordinate system to another. But if they satisfy certain relationship in one coordinate system, that means it will be true in other coordinate system. The other interesting arithmetic operation is what's so-called contraction of indices. That means I sum over some indices. I make sum two upper and down indices. One of them is equal to another. In that way, I make summation over that indices. And this is a very interesting tool, interesting arithmetic operation, and we will see an example. For example, if I take Vm Gmn equal Vn, and here I start from contravariant of order 2 tensor, I'll multiply by tensor of covariant of range 2, of ring 2 Gmn, and I get covariant tensor of ring 1. In general way of speaking, contraction operation is lowering down the ring of a tensor. For an example, and also it allows us not only to do that, also it allows us to low up or low down indices. Tmn, for example, using some contraction, I multiply by GMR, which is contravariant, GMR, multiply by TRN. I make summation or contraction over R. I will get TMN, which is mixed of type 1,1. So generally, when I am talking about tensor, they have set of component. This set of component could be covariant, but also I can find one-to-one corresponding to other set of component, which make this tensor contravariant. I mean, being covariant or contravariant, they are expressing more or less the same thing, but in different way, in different set of component. Because once I know the metric GMR, I can jump from one to another. For instance, the metric in Cartesian coordinate, for example, when there is a flat, then ds square equal to delta mn dxm dxn. This is in Cartesian coordinate. Okay, so in more general case, I take it gmn dxm dxn. But also this could be written instead of taking the metric as covariant tensor, which is the general case, I can take it contravariant way, gmn dxm low dxn low. I mean, this is also other way of writing the same tensor, the same metric. So for every tensor, it is possible to find corresponding set of component to pass from covariant or representation to contravariant representation of the same tensor. Also, it is different tensor, but I mean, once you know the metric, you can jump from one to another. So there is no additional information you need beside the metric. Once you know the component of the tensor, you know the metric, then the contravariant associated tensor is just a result will be given just by some calculation. In general case, for example, about contraction, an example about contraction, let's take, for example, a tensor of type 4,3. That means I have 4 indices above and 3 indices down. Then I make summation, I make one of the indices up is equal to one of the indices down, which is that contraction arithmetic. Then I will get NRA above and BQ down. That means, what does that mean? I get another tensor of type 3, 2. I started from tensor of 4, 3 and I get 3, 2. So this is what the process this process of contraction allow us to lowering down the rank of a given tensor. Another example, if I take a tensor of type 1, 1, TMN, then TMN using some contraction, I have just one possible way to do the contraction, is equal M equal N, then TMM. TMM is just what does that equal? Equal T11 plus T22 plus T33 and so on. And finally it will be just a tensor, a scalar. Another interesting example, which is everyone use it from the beginning of elementary school, but we use it in, it's what's so called scalar product. If I take a tensor of type 1, 0, which is vector, and tensor of type 0, 1, which is its transposant, which is just, and make the contraction over the indices M equal N, then I will get exactly a scalar, which is the scalar product. In more general case, for given tensor of type BQ, then this type BQ, for example, if I take 2, 2, type 2, 2, then TRS above MN down in Y coordinate system, it will be transformed to X coordinate system by multiplying by mix it above, mix it dx over dy or dy over dx. According the number of H1 is according to the P and Q. So for example, if I take 2 by 2, then dx alpha over dym be dx beta over dyn multiplied by dy r over dx gamma multiplied by dys over dx theta. Then I have t alpha beta t gamma theta above, alpha beta down in x coordinate system, and so on and so on and so on. And very interesting example of metric tensor is Minkowski metric tensor. In special relativity, we deal with what's so-called Minkowski space, which is general or natural generalization of Euclidean, but with very important difference in metric. In Euclidean, we take the metric as ds square is equal to dx1 square plus dx2 square plus dx3 square and so on. But using Lorentz transformation, Lorentz transformation tells us that the only invariant quantity is what's so-called proper time. Proper time is equal or represented by d tau square is equal to tt square minus dx square, where here dx is all space axes. I mean, not only dx minus dx square minus dy square minus dz square, and in more general case in minus dxi square. But using Minkowski space, that means I take x, y, z and time, then dt square minus dx square minus dy square minus dz square. This minus is very meaningful here, and we will see that later its role in proving what's so-called time dilation and length contraction. But what matter here that the amplitude of all of them are equal 1. So, and here we use d tau square to express this metric, g mu v dx mu above dy dx nu, and here we use Greek letter. That means we are talking in space time, and starting from 0, 1, 2, 3. And also this all of this convention are invented or used by Minkowski and Einstein when they put their definition, and then it became like convention. So this metric G mu nu in Greek, that means as I'm talking about space-time, is written as 1 0 0 0. I mean it's diagonal, and in the diagonal is 1 minus 1 minus 1 minus 1. And here it's interesting to mention that this is just also convention. Maybe the opposite will happen. I will start by minus 1, but all of the rest will be plus plus plus. So the relationship between the time and spatial dimension should be the opposite. There is minus between them. In order to, we will see later its importance here. So this tensor is covariant as we proven previously, and of range 2 because I have two indices. This tensor, this metric tensor, is in Minkowski space. I mean it's Euclidean space. I mean it's boring static space. But what happened in actual universe, what the expansion universe? Let's take about the metric there is time independent, but it is place dependent. So the metric will be written, for example, if we are talking about accelerating a universe, then I have to put, instead of taking minus 1 minus 1 1 minus 1 on spatial axes, we need to take minus 8a minus 8a minus 8a. Then the proper time will be written in a bit different way, which is dt square minus a square bdx square minus et square dy square minus et square bdz multiplied by dz square. So what is the affection? I mean, how can we express this, extract the physics behind this metric? To find, we need to understand the rule of the coefficient in front of dr square, for example, or d theta square, or dx square, or d theta, or dt square. Let's imagine polar coordinate, and we proved previously that the metric in polar coordinate is given by ds square is equal to dr square plus r square d theta square. So this is a plane. Why? Because I know that the relationship between theta and r, if I take theta, if I increase theta, that means if I make the line constant of theta theta is perpendicular to theta to line constant of r. If we imagine another metric, for example, if I take ds square equal dr square plus sine r square d theta square, then this is a sphere, or more precisely, it's a surface of a sphere. Why? Because sine r will be increasing function between theta and pi over 2, and then it will be decreasing function between pi over 2 and pi, and this is the interval of the possible value of theta between 0 and pi. So half of it will be increasing and half of it will be decreasing, and this is exactly the case of surface of the sphere. And let's imagine, for example, if I take, instead of ds square equal dr square plus exponential r d theta square, then this will be horn. I mean, it will be horn. It will be start from 0 in r0, and then will be increasing very fast. So it will be like a horn. And this is a notation about the shape of the universe, and it is discovered little by little. I mean, Einstein supposed that it is statistic universe, and then later, namely Edwin Hubble, proved that we are living in expanding universe, and then we need to reconsider this this form or this equation in order to introduce some constant in metric, in order to take that into to explain the experimental astrophysical observation.